All right, let's jump right in. Have you ever stopped to think about what something like a diamond, gasoline, and, oh, I don't know, the soap you use every single day have in common? Today we're diving into the one element that connects them all, carbon. We're going to break down how this one little atom builds, well, pretty much everything around us.
So let's start with a little puzzle, right? When you first think about it, these three things, they couldn't seem more different. I mean, you've got the hardest substance on Earth, the fuel that runs our cars, and the stuff we use to wash our hands. So what in the world is the connection here?
Well, the answer, as you can see, is carbon. You can think of it as the ultimate multitasker of the periodic table. It's the element that forms the backbone of, well, almost everything, from the fuel in our tanks to the very DNA inside our cells. So here's our game plan for today. We're going to start from the ground up, literally from the atom itself. First, we'll see why carbon is such a fantastic builder. Then, we'll dive into what I like to call its social network of bonds. After that, we'll explore the universe of compounds it can create, peek into its chemical cookbook, and wrap things up by looking at how it helps us get clean.
Okay, first up, carbon, the ultimate builder. So really, how does one single element manage to do all of this? To get it, we've got to zoom way, way in, right down to the atomic level.
It really comes down to two key superpowers, if you will, catenation and tetravalency. Now, catenation, that's just a fancy word for carbon's ability to link up with itself, to form these super long, stable chains and even rings. Kind of like a molecular Lego set, you know? And tetravalency, that just means every carbon atom has 4 connection points, 4 hands ready to link up with other atoms. It makes it an amazing connector.
So how does it make all these connections? Well, it's all about sharing. Carbon isn't really into giving away or stealing electrons from other atoms. That's just too much drama. Instead, it forms these really strong, really stable connections by sharing its electrons. We call these covalent bonds, and they are, no exaggeration, the absolute foundation of all organic chemistry.
All right, so we've got the fact that carbon loves to form these strong, shared bonds. But the next piece of the puzzle is how it shares. Because, you see, the type of bond it decides to form can completely change everything about the final compound.
And this whole sharing thing, it gives carbon compounds some really unique properties. Let's compare. You've got ionic compounds, like good old table salt, where electrons are actually transferred. They have super high melting points. But then you have covalent compounds, like wax, and because they're just sharing electrons, they have low melting points and don't conduct electricity at all. It's a totally different ballgame.
And the differences don't stop there, not even within carbon's own family of compounds. So if a compound only has single bonds between its carbon atoms, we call it saturated. You can think of it as being pretty stable, pretty chill. But if it has double or even triple bonds, then it's unsaturated. And those extra bonds, they act like little chemical hotspots, just waiting for a reaction. It makes the whole molecule way more reactive.
Okay, so we've got carbon making chains, and we know it can have different kinds of bonds. The next step up in complexity is when we start attaching other groups of atoms to these chains. It's kind of like adding accessories to an outfit. These little attachments can give the entire molecule a whole new identity and a totally different job to do. These accessories are what chemists call functional groups, and they really do define the molecule's personality. For example, if you tack on an OH group, boom, you've got an alcohol. If you add a COOH group instead, you've just made a carboxylic acid. This table just shows a few examples, but each one of these groups completely changes how the compound is going to behave. So once we have all these different compounds with their various functional groups, the real fun begins. We can start to transform them. And this is where carbon chemistry really does become like a cookbook. There are a few essential recipes or reactions that let us create millions of different molecular dishes. First recipe on our list is one you're definitely familiar with, combustion. In simple terms, this is just burning. When you burn a carbon compound in oxygen, it releases a ton of energy as heat and light. It's the reaction that's happening when you start your car or light your gas stove. Next up, we have the addition reaction. Now remember we talked about those really reactive, unsaturated compounds, the ones with the double or triple bonds? Well, with this reaction, we can add hydrogen to them. This breaks one of those extra bonds and makes the compound saturated. And believe it or not, this is exactly how they turn liquid vegetable oil into solid margarine. And now for a really sweet one, esterification. This is what happens when you react a carboxylic acid with an alcohol. The result is something called an ester.
and esters are famous for their amazing smells, often really pleasant and fruity. This is the reaction that gives us the natural aromas of things like bananas, pineapples, even a lot of perfumes. All right, let's take that idea and build on it. We're going to see how one specific carbon reaction leads to something we all use every single day. We're moving on from fruity smells to the chemistry of clean, how we make soap.
So this process has a pretty cool name, saponification, and it's basically the recipe for soap. You take an ester, in this case a fat or an oil, and you treat it with a strong alkali, something like sodium hydroxide. And what you get out of that is a simple but really, really powerful cleaning agent.
Okay, so how does soap actually get things clean? Well, the magic is all in the design of the soap molecule itself. It's got this long carbon chain with two totally different ends. One end is the hydrophobic tail. It hates water, but it loves oil and grease. The other end is the hydrophilic head, and it loves water. This split personality is its secret weapon.
So check this out. When you mix soap with water, the molecules automatically arrange themselves into these tiny little spheres called micelles. All the water-hating tails dive into the center where they can grab onto any dirt or grease. At the same time, all the water-loving heads stay on the outside, forming a shell. This basically traps the dirt in a little bubble that can then be easily washed away with water. Pretty clever, right?
So when you take a step back and look at the big picture, it's actually incredible. We started with a single atom and its ability to form 4 bonds, and we ended up with the complex chemistry that lets us wash grease down the drain. It's a perfect example of going from something super simple to something incredibly sophisticated.
And it really all boils down to this: carbon's unique talent for forming stable chains with itself and for making 4 distinct bonds. That's the whole reason it can create this mind-boggling number of different compounds. Those 2 simple rules are the foundation for all the complexity and diversity we see in the world. So, I'll leave you with a final thought to chew on. Now that you know some of its secrets, just take a look around you. The plastic in your phone, the food on your plate, the clothes you're wearing. What other parts of your daily life do you think are built on the amazing backbone of carbon?